So welcome back to the second part of the morning session. We have Bernd Hinrichsen that will show a bit more or give more insight on synchrotron related technique. And at 11, we will have someone from ESRF discussing how to apply for beam time and give some insight for a good proposal. So I will say, Bernd, go for it.
Fantastic. Thank you so much. I'll try and share my presentation. Let's see if this works. One sec. So, do you see my screen or my presentation
Yes,
at least? Wait,
but we have Zoom that, yeah.
does it look okay now?
It looked like very small.
Oh, okay. Let me see if I can.
Yep,
Okay,
that,
great.
that's full screen
Okay.
now.
Okay, so I'm going to talk a little bit about myself as well and my career within industry and how I made my way to where I am now. Yeah, and this was suggested by Reynier, and I think it's a nice idea. Um, I've presented it now and again to students, sort of just to give them an idea about what sort of paths one can end up taking and being also a satisfied person in the career as well. So a lot of my slides have BASF on them, and then second part will not have BASF on them anymore because that's sort of my process I'm going through at the moment. But it all starts out a long way back when I was born, and I was born in a very small town in the north of Namibia. Now that's a country, a very sparsely populated country in the southwestern corner of Africa. And Namibia has some probably more warthogs than it has inhabitants. Yeah, it's a very beautiful country. I can recommend you to go there. But it is also a big has also great mineral resources. And I was born in a little mining town in the north, which at the time I think was one of the largest copper mines in the world. Yeah. And what was quite special about this town is that they brought out a lot of very interesting and unique minerals out of the mine. So it is very well represented in all the mineralogical collections around the world and also the museums. So if you look around, you'll see minerals from Tsumeb all over the place. Yeah, so next to Minas Gerais, it's one of the most popular sources for spectacular minerals. Yeah, mainly also copper and arsenic and silver um, minerals from there. But my parents moved away from there very soon. Yeah, so the next picture gives you an image of the way I looked at the city that I grew up in. Yeah, from basically on the mountain where my parents had their house, and this city you probably know better by its skyline, its other skyline, which is this. Yeah, so this is Cape Town. And I grew up, or was lucky enough to grow up in this beautiful city. Yeah, as you can see, it's at the ocean and has stunning mountains right in the center of the city. Yeah, 1,000 meter high um, Table Mountain, and it has a huge coastline because it's a peninsula. So it is just about, yeah, offers everything that your heart can desire as a young child growing up in a and going to school. However, I must admit I did grow up during the apartheid era, so I only sort of later, in my adolescence, started to comprehend what was happening in this weird society in which I was growing up, and it was a quite a spectacular ending to it in '94, which I also um, was there and to understand part of it, yeah, of how it happened. So great great memories of the nature society in change and tumult as well. So it was a really exciting part of my life. But then I finished school there and decided to move to Europe to do my studies. And this is the city that I went to. Yeah, it's also got a bit of water. Yeah, it's on the Rhine, and it has something spectacular about it, but that's man-made in this case. It is the cathedral in Cologne. Yeah, and that is a very fun city to study in, I must admit here, even if it did probably elongate my studies by a few semesters, because of the nightlife being so spectacular and the carnival being quite something, quite an event. This whole week of uproar in the city, yeah, and no chance to get any studying done in that week. Um, and the studying I did in this little institute, which is really cute, and it actually still exists today. I was quite astounded. I went there to visit a few months ago, and it's been nicely renovated, and it's still there, and still got the nice Japanese garden in the inner courtyard. This is the Mineralogical Institute of the University of Cologne. And that is where I went to study because I admit I started studying something that I didn't feel very attached to. For 2 semesters, I was studying actuarial science, so insurance maths for those that want to know the nitty-gritty. And that's somehow didn't tickle my fancy. And I decided to look around and see what else the University of Cologne had to offer. And I found mineralogy. And seeing that I was born in a place which is renowned for its minerals, I thought, oh, that might be a fitting thing to study. Plus, it's a natural science, which is what I wanted to get back to because I am so fascinated by research. And then I found this Mineralogical Institute, went to visit the prof, and then I had decided that this was going to be what I wanted to study. Yeah. And and I'm very grateful for it as well because it's such a beautiful topic to work on. Yeah. Um, from there, I moved to Stuttgart. Yeah. So many years later, I'd sort of finished my studies in Cologne and I'd actually started working or and seeing it was like end of 90s, beginning of 2000s. It wasn't sort of super easy to find a job in mineralogy. Yeah. So I'd taken up a job, which was basically my student job, which I'd done in parallel to studying. Seeing I was fascinated by the internet coming up in the 90s, I wanted to figure out, or I wanted to learn how it was held together and how um, it was made in the basics. And so I went to work at the local computing or the university's computing center and worked there all my student life. And then I just got a job as an IT specialist, a network and systems administrator in a small company just north of Cologne in Leverkusen. And I worked there, set up their email system because they had a very sort of scruffy network. Yeah, I put it, and I made it all nice. And then I spent 3 months doing that, and I was centralizing things and getting it all sorted. And then I started getting really bored. So I went back to my prof in Cologne and said, "Hey, can't I do a PhD? I mean, what an exciting job when I'm finished." And he said, "Yeah, sure, come, but I don't have any money." So I tried to do like a part-time PhD and part-time working on the side, but that was a catastrophe. And then I remembered, okay, there's Stuttgart. There's this guy in Stuttgart. He had held this brilliant presentation um, in Cologne when I was there, and he was doing powder diffraction, powder X-ray diffraction. That has a lot to do with crystallography. That'd be cool. And then I sent him an email, hey, looking for a PhD position. How about it? Do you have some openings? And he said, yeah, come visit. And I went to visit, and I was convinced, and they were convinced, thank God, that I was a right fit. And then I moved to Stuttgart, and this is like sort of the picture. of Stuttgart in its most beautiful. It's settled between some hills, and it's got some nice old palace buildings that are taken over by the finance ministry of all things in Stuttgart. And but the place that I was doing most of my work was slightly at the edge of Stuttgart. It was this place, not quite so nice unless you like brutalist architecture. Um, it is the Max Planck Institute for Solid State Research. And Max Planck Institutes are great places to do your PhD. So in contrast to the University of Cologne, Max Planck Institute had loads of money. Yeah, so there was no discussion about, if we can pay you or not. And you could do all sorts of fantastic research. Think up experiments that you wanted to do, then speak to your advisor, and the money was there. It was always, a fantastic place to do research. And this was where I started visiting synchrotrons, to do my experiments. And because the guy that I was my supervisor, who's a good friend still to this very day, Robert Dinnebier. Is a great expert in powder diffraction and well connected with synchrotron research, because he'd done his PhD at a US synchrotron in Brookhaven, close to New York City. Um, and then I was spending a lot of time doing experiments in various synchrotrons, and got to um, learn to love the brilliance of the X-ray sources of synchrotrons, in contrast to what we had back home in the laboratory. Yeah. From there, I did my PhD really quickly then, because my first child had been born already. Aurel was 2 years old when I moved to Stuttgart with my family, and my second son was born during my PhD. So I had quite a bit of pressure to start getting the finances in order. Even though I had a job that was paying okay, I still had accrued a little bit of sort of student loans that I had to pay back. In those days, one still had to pay back the very friendly German loans that you got. Even though tuition is free in Germany, living is not, and then you can get BAföG from the German states. And anyway, I had accrued that, and I wanted to pay it back. So I decided to go straight into industry from my PhD, and I was lucky enough to end up here at this company called Bruker. They are I think in the meantime, one of the largest analytical instrument builders. Yeah, they started off in Karlsruhe building NMR spectrometers, and then they started expanding in the 90s. And they haven't stopped. So now they're a huge company. I worked in the small X-ray part, which used to be a part of Siemens, an old German industrial giant. And they sold off this X-ray analytics part because it wasn't sort of core business. And Bruker bought it up, and that was 1999, and they bought it. Well, by the time that I joined in 2007, they had grown from 100 people to 300 people. I think there are a lot more now, but it was a great time to be there. I had a wonderful, wonderful time working with scientists, with challenging X-ray scattering problems, wanting to understand the structure of the materials. And my job as an application scientist was to explain to them how Bruker instrumentation, of course, could solve their problems, and show it to them, measure their data for them, analyze their data, but also then, and that was one of the most fun parts of working for Bruker, was traveling and teaching. Yeah, so I did spend quite some time in the Far East, so in Korea and Taiwan, teaching powder diffraction, and also in Poland and in Bulgaria. So I had a great time traveling around, teaching what I could do best, powder diffraction, and therefore I really reminisce quite fondly about the time that I was at Bruker. But as I was working at Bruker, I got to learn about one of their customers. And I got to know them quite well, and that was BASF. And when they phoned me up in 2010 and asked me if I knew anybody in my network that would be interested in taking over the job of running their powder diffraction lab, I said, yeah, absolutely, I know somebody. And so I started in January of 2011 at BASF, running their powder diffraction laboratories. Yeah. And now this was right in the middle of what is still the largest chemical plant on the planet, in Ludwigshafen, just opposite the Rhine from the town of Mannheim. And Ludwigshafen is a city which only really exists because BASF founded their first factories in Ludwigshafen. Yeah, and everything that you see here on this image is their factory site. I don't know. So what you see is my microscopy. That's where I was situated, in this beautiful old building, which was called M300 in the as a name because everything has a letter and a number associated to it. So that's how the addresses work on this site. And that building is the building where the Haber-Bosch process to create ammonia was developed. Yeah, so it is a very historical building, and I had my office on the second floor in the corner, which was really fantastic. And that's where I was for the time where I started all the or did most of my work in analysis. And I had the pleasure of working with these people, yeah. Um, and I was running the X-ray diffraction lab, but I was also responsible for the electron microscopy and solid state nuclear magnetic resonance laboratories. Um, and I worked together with Murat over here, with Philip and Hubert and Carsten for the longest time, and it was great. You know, I got to build up, I think, one of the strongest electron microscopy laboratories in industrial research. Plus, also take care that our X-ray diffraction lab was a really strong and powerful unit. Um, and and making sure that solid state NMR still existed in the company as well, because that was, I mean, of course, a very expensive technique to keep going, but incredibly valuable with respect to the information that you can extract out of your materials using that method. Yeah. Here's some of the work that we were doing within BASF. So just giving you a rough idea so that you can understand how much fun and at what level of detail you can still work in industry in. Yeah. And what we looked at over here was some cathode active materials. These are some battery materials, and there we used our microscopy capabilities to understand surface degradation. Yeah? Now, this is one of the things that are most important to understand when you're looking at cathode active materials and trying to understand how they differ from each other dependent on how you produce them. Yeah. So our battery colleagues were always trying to make the best possible cathode active materials using the most efficient resources and producing them in the most resourceful way, and then to understand how that impacts their electrochemical also how it impacts the structure, and how that structure then impacts the electrochemical properties of the materials. That is where we were sort of producing the most benefit for BASF. And here we looked at in detail using our very, very nice corrected microscope, which had an atomic resolution that you see here, how the surface was degrading, and how that could be changed, for example, using a coating. Yeah, and here you can see at the bottom image, you can see an elemental distribution of different elements that are used for coating, and in the top you can see how that impacts the surface structure of the cathode active material. Here, for example, we were also looking at catalysts, because BASF doesn't produces basically everything. Yeah, it's a huge chemical company that has a myriad of different business units and also factories. Yeah, that produce different materials. Yeah, some of them also obviously are corrosion related or corrosion inhibitant related. But this one is an acrylic acid catalyst. And we were trying to understand the structure of this material. Now, it is a very two-dimensional material, and you can see very nicely that you can even see the structure of this, sort of the individual atoms making up this two-dimensional layer over here in this bottom image. But you can also see, if you zoom out a bit and you do an elemental mapping, how the distribution of various different elements, which are color coded here, are how heterogeneous, yeah, this actual material is. And there've been quite some interesting work to understand why it is necessary in the process that it is so heterogeneous. Yeah. So this is not a fault. This is a feature of this acrylic acid catalyst. Yeah. Um, it's a very fundamental catalyst. Yeah, because it takes one of the feedstocks that come out of our very very basic steam cracker. Yeah, which takes natural gas and reduces that to smaller chained carbon molecules, and this acrylic acid catalyst takes the propylene, oxidizes it to acrolein, and then hydrogenizes it to acrylic acid, which is then useful for further chemistry. Yeah. Um, and another thing that we did in the microscopy field was um, to understand particular products, because nanomaterials was a huge topic for a long time, and we wanted to be able to make sure that we can characterize nanomaterials properly. Yeah, and the best way to do it is to put it under a microscope, and then to let an automated image taking collect very many images over your material, or over your sample holder, and then also to analyze these in an automated way, so that you reduce the biases that you otherwise get in if you have an operator taking all of these images, right? So we developed some machine learning models, which then ran over these images, analyzing the shapes and the sizes, and then giving out a decent report that is with as little bias as possible, to give you an idea, is your material a nanoscopic material or not? Yeah, that is a very important for REACH classifications and the European chemical market. Here's something cute. I just put it in because I thought this image was so cool. These are electronic materials. Yeah. So as I said, BASF does a lot of stuff, and amongst one of these things is materials for the electronics industry, and to make sure that we understand our materials do what they have to do, we took these semiconductor structures. Yeah. that had been put onto a silicon chip and cut it with a focused ion beam, scanning electron microscope, and then imaged it in the transmission electron microscope. And there you can see how fine these structures are in modern semiconductors. Now, so you really see these features that are below around about 2 nanometers in size. So brilliant capabilities, and that's something that you really need a very decent electron microscopy for. Now, a lot of what we focused on because my area of expertise, or my area of analysis was focused a lot on these battery materials, because that was a lot of research going on there, is to do the microstructural analysis of these battery materials, and these were the materials that we were looking at. Now, it started off with a sort of standard nickel, cobalt, manganese materials, and then ended up into high nickel, and in the meantime high manganese materials, and from this year onwards, actually this roadmap is quite astoundingly accurate. Seeing it was done back in 2017, we're looking more strongly into what comes after lithium. Yeah. Because this is sort of the process that these materials have to go through. Yeah. So these cathode active materials are precipitated out of a solution, then they are calcined with a lithium source, and then coated and tested afterwards, then with respect to how well is the dopant distributed, and how is the coating. How does the coating look on the surface of this material? And there we had to be able to even see monolayers of coating on this material. So only one atom thick layers on one of these materials is something that is very challenging to do, but is something that can be done with high resolution transmission electron microscopy. Of course, also there are other surface sensitive techniques, but in the case that we were looking at, it was TEM. Here again, there's the process that you have to go through. Yeah, you get the precursor material that is precipitated. You mix it with your lithium source and dopants, and then calcine it at anything from 700 degrees upwards. And then afterwards, there are coating processes and washing processes, and then and every part of this step, we've got methods to try and understand what is happening in this process. And this is why my job was so interesting, because this is just one example of where the microstructural analysis sort of had to give some feedback, but it sort of offered a huge variety of different challenges. Yeah, and this is one of the ones that I've enjoyed a lot during my period, is looking at these materials that seem very simple at the beginning, but then turn out to be quite complex. Yeah, so what we looked at was the precursor material. Yeah, so what happens is you mix sulfates of the metals as a solution. So the cobalt, nickel, and aluminium sulfates in this case, you just mix them together, and then put it in an ammonia solution. So it's a very high pH, and then you precipitate the materials out, stirring very, very, very strongly, so that you put in a lot of energy, and you precipitate out nanoscopic materials, or nanoscopic crystallites that are all bunched together into microstructural spheres. Yeah, and what happens is that you make these layered hydroxides, yeah, that are relatively crystalline, but they're full of stacking faults. Yeah. So you see, if you try and model this with a crystal structure that is perfect, yeah, you end up with a crystal structure that is perfect has also perfect peaks. Yeah. They're perfectly shaped and they're nice and sharp, and you can model perfectly crystalline materials very, very nicely using a very standardized model. However, if you've got stacking faults and disorder in your material, you end up having peaks that are very, very individual. Yeah, let's put it that way. Yeah, so some are broad, some are sharp, some are asymmetric, and there's no way that you can manage to fit anything sensible using a standard model. So this is what a standard model looks like. The the blue dotted line is are the data that we collected, and you can see the mismatch is huge. Yeah, that's the gray line at the bottom here. So the mismatch is gigantic. However, if you manage to describe your stacking faults, yeah, you can match that those very disorderly looking peaks quite beautifully. Yeah. So that's what you see in the second picture over here. Yeah. You take a supercell model and you calculate the probabilities of various types of stacking faults occurring. And then you can end up with a calculated pattern which is astoundingly close to what you actually measure. Yeah. And when the first time I saw this, this was done in collaboration with Sebastian Better. He was doing his PhD at exactly the same institute with exactly the same supervisor that I did my PhD with. So it's always cool to keep your network alive. And I knew that he was an expert at describing stacking faults. And once I saw this pattern, I said, "Okay, this is something for Sebastian." And I rang him up and said, "Hey, how about looking at a battery material?" And he was quite keen. And so I gave him the data, and he looked at it, and he came up with this model, which in my mind is absolutely brilliant at describing the real structure. And then we managed to look at it under a microscope. Now this is super challenging, right? Because it's a layered hydroxide, yeah. And if you look at it under the microscope, under an electron microscope, that stuff just disappears under the electron beam, yeah, because the electron beam brings in so much energy into the sample that it changes, yeah, under this electron beam. But we tried and tried and tried and fiddled and fiddled and fiddled and got the properties or set the electron beam properties so that we could actually measure these disorders. And you can see all of these slippages and these shifts and the intercalations that we put into our theoretical model to match the X-ray diffraction, and we could verify that we actually do see them in the real life image of our materials. Yeah, that was very satisfying. Yeah, and what happens now? So, what is all this good for? Yeah, um, you can match that properties. So this microstructural um, uh, characteristics to the final electrochemical properties. Yeah. So we can see that the more defects we have, the weak in our precursor material, the less good our final cathode active material is going to be. Yeah. So the cycle life is very strongly affected by the stacking defects that come in right at the beginning of the process of producing these materials. Yeah. So knowledge is always a powerful tool to use when you're trying to optimize your materials. Yeah. Some people might have thought, defects don't matter because we heat it up so high in the end, but we showed that the defects right at the beginning do matter. And this is another experiment how we worked at the synchrotron, and how we developed a setup to measure the precipitation in situ. So as it happens, yeah. So when you make these materials, yeah, I mentioned that you put in ammonia and these sulfates and then precipitate, and we wanted to watch how this actually happens in real time. And so we went to the synchrotron, and this is a big picture of the synchrotron setup, and we built a special sample environment, yeah, where we could have a large volume um, of material that we were stirring and we were dosing, but we also had a very small window where the material was passing by, so we could actually measure a diffraction pattern. And this is the diffraction pattern of what we measured, yeah, um, with the materials in situ in the in situ setup. So this is what a time-resolved diffraction pattern looks like here. The peaks just get colors. So the higher the peak comes, the more red the color goes, the lower the intensities are, the bluer the colors. And this is the number of hours that we spent measuring, and this is the diffraction angle, yeah, that we were measuring at. So this is a picture of what you can do. Yeah. Another thing that we did was to measure the orientation and representation of the materials of the crystallites in the ball. Yeah, now I mentioned that all these crystallites are stuck together in a secondary particle. And what we did is analyze how the orientation changes depending on how you synthesize the material. And that was also an extremely interesting piece of work where we discovered a lot of how we can influence the way crystallites sort of grow, um, and how that changes with the way we synthesize the materials. Yeah, this is another really cool aspect of the green revolution in BASF. So that is methane pyrolysis. We take methane, we heat it up to 900 degrees methane gas, and run it over a 900 degrees temperature substrate of carbon, and then the methane cracks. The carbon is deposited on the substrate, and the methane goes up. Sorry, the hydrogen goes out through the chimney and can be used then um, efficiently to for other chemical processes. Yeah, for example. And this method is a really efficient way of reducing the CO2 footprint of standard hydrogen production. Plus, it's way more efficient than splitting water. Yeah, so you need about 9 times less power to run this process than it costs to split water. So this is a really cool way of producing hydrogen. And we were looking at the carbon to try and find a good use for the carbon afterwards as well, because you do obviously produce a huge amount of carbon relative to the amount of hydrogen you produce. And finding a good use for the carbon is then essential to make this process sustainable. Um, Okay, I think I'll skip this part now because I want to get through to the synchrotrons. And this is something that you'll see in the next talk as well. This is a picture of the most wonderful synchrotron facility in the world, which is in Grenoble in France, in the southeast of France, settled between two, or settled in a valley with mountains around it. It's a really beautiful place. I can recommend you to go if you have the chance. This is where we have been building up momentum transfer, and that's the next step in my journey. So I am exiting BASF tomorrow. Very exciting time for me. And I'm going to, or have been full time already on this momentum transfer, but it's changing from a project within BASF to a real own company as of tomorrow. Yeah, and the people that are doing this with me are Sebastian and Maxwell. There are two researchers. Sebastian was a laser physicist, but he's been building companies for the last 15 years. Max has been a researcher all his career, and he remains our central research capability in momentum transfer. And there's me, yeah, and we are building momentum transfer. Our thing is to do extremely high throughput X-ray diffraction, and we prepare our samples in a special sample holder to enable an extremely high sample changing frequency. Each sample gets prepped into this 2 millimeter by 1 millimeter sample volume area, and it gets its very own QR code so that we can identify each and every sample that goes through our system. This is what the system looks like. Yeah. So the sample sticks are over here. Yeah. They get pushed through the sample holder, and the X-ray beam goes through each individual sample holder, and it hits this this beam stop. Yeah. This beam stop is important so that the super brilliant synchrotron X-ray beam doesn't damage this very expensive detector over on the left that you can see, which costs a lot of money, and is very, very sensitive to X-rays, and that's where we collect all of our data. Now hang on, they do work here. This is what our sample holder looks like in real time. This is how the light is supposed to represent the synchrotron light. This is just outside of the hatch, and this is how our samples get measured. Yeah, and over here we did a high throughput test just to see how long it takes for us to switch from one measurement to the next. And as you can see, it is quite fast. So we can switch from one sample to the next in 0.1 seconds. That is including reading all of the QR codes and everything. Yeah, this. Hang on. I hope you can still see this. This is how we typically do our measurements. So we measure one set of patterns for X-ray scattering and one set for total scattering pair distribution function analysis. The good thing about the second measurement is that you can analyze very disordered material, but also I think I have to switch back. Yeah, very disordered material, but also amorphous material. Yeah, using this total scattering PDF method, you can get information about the local structure, so how the atoms or the molecules are arranged relative to one another. Very important for BASF with respect to understanding polymers, yeah, or very disordered materials. Also, glasses can be very nicely described using this method. Here is how our setup basically works. You get this brilliant X-ray going through your sample, and then scattered. We measure on a big two-dimensional detector that I showed you, and we can measure a relatively big area in the scattered space. So we can do all sorts of analyses, sort of structural analysis, using X-ray diffraction, understanding the crystal structure or the so the crystal structure where the atoms are relative to one another, but also understanding how the crystallite sizes change. And the setup makes data really easy to analyze. Yeah, and this is one of the reasons why I decided to create momentum transfer, because the data was so brilliant that I had to get it out to the rest of the world and not only keep it within BASF, which was originally the project that I designed. The total scattering that I mentioned, we have a really cool data pipeline where we can generate pair distribution function histograms, giving you the atomic distances to one another, to make it very easy to understand amorphous materials and nanostructured samples. And we even have the capability at this hatch to measure small angle X-ray scattering, which is great if you want to understand pore structure, for example, in porous materials like zeolites, or particle size distribution of nanoparticles. Yeah. This is what our X-ray diffraction patterns look like. Yeah. So nice sharp peaks. This is a standard material. Obviously, it has very nice sharp peaks. And this is the refined data are in red. The blue data are the measured data, and this is the difference plot in gray. So it's absolutely brilliant quality. This is what it looks in comparison to laboratory instruments. Here again, my reasoning why I wanted to make this available to everybody, because this data is just so amazing. It has to go to be made available to researchers everywhere, and this high throughput setup makes it possible to really analyze large data sets or large number of samples, which can be very, very useful, especially nowadays with the onset of artificial intelligence and machine learning to analyze data and to understand data from and understand the structure property relationships. And there you can go straight from your data to your properties without having to set up the whole analysis pipeline in between. Yeah. And this is what we've got in our goals. Yeah. So we can already measure thousands of samples every day. And our goal is to make that possible for people and trying to understand how that relates to their final properties. Yeah. And with that, I'm going to come to an end. I thank you very much, for your attention.